So till now we discussed many basic concepts which are related to our electromagnetic theory and which are useful for our electromagnetic theory. So all these concepts are very much useful in solving mathematical equations of our electromagnetic theory. So what we have to do is we need to apply all these concepts in different ways in our electromagnetic equations. So what we do is initially we will discuss a few model problems based on all these basic concepts which are related to coordinate systems, vectors and calculus. So if we know how to apply all these concepts in different ways, then easily we can solve many problems in our electrostatics, magnetostatics or electromagnetic theory. So what we do is in this session we will solve few model problems which can give us a little idea or a thorough idea about different concepts which are related to coordinate systems, vectors and etc. etc. So what we do is we will start all these concepts with a simple problem. So a question was given like this. Consider vector field A bar, the closed loop line integral of A bar dot dl bar can be expressed as option A, double integral which is closed del cross A bar dot ds bar over the closed surface bounded by the loop. Option B, a triple integral which is closed del dot A bar dv over the closed volume bounded by the loop. Option C, open volume integral of del dot A bar dv over the open volume bounded by the loop. And option D, double integral which is opened, double integral del cross A bar dot ds bar over the open surface bounded by the loop. This is the question given to us. Now the given vector is A bar is a vector which is given to us. He asked what is the equivalent of closed line integral of A bar dot dl bar. Now we need to identify the equivalent of our A bar dot dl bar. Now the different options are given to us. Now we need to examine which option is most suitable to it. So before that, just recollect the concepts which are given in our Stokes theorem and divergence theorem. Stokes theorem, which is a theorem which is useful for relating our line integral with surface integral. So if we have any vector A bar, how the Stokes theorem was defined? The closed line integral of A bar dot dl bar is equals to, so you can take the equivalent of open surface integral of del cross A bar dot ds bar. So whenever there is a line integral which is closed, clearly remember that for a closed line integral, A bar dot dl bar can be equated to open surface integral. So here you need to remember it in a simple way, that whenever you have a closed line, let us take this is a closed line what we have. Always a closed line will form an open surface. So the closed line will be related to the open surface only. So the closed line integral of A bar dot dl bar is equals to open surface integral of del cross A bar dot ds bar. Now check for the options. If we check the options, option D is right, that open surface integral of del cross A bar ds bar over the open surface bounded by the loop. So for this particular problem, option D is right. But if you check the remaining all options, in the option A also we have the same one, but it is the closed surface integral. That is closed surface integral of del cross A bar dot ds bar. Since it is a closed surface integral, option A is not right, option D is only the correct one. So if a vector field V bar is related to another vector field A bar through V bar is equals to del cross A bar, which of the following is true? Note, C and SC refer to any closed contour and any surface whose boundary is C. Option A, closed C V bar dot dl bar is equals to double integral SC A bar dot ds bar. Option B, closed C A bar dot dl bar is equals to double integral SC V bar dot ds bar. Option C, closed contour integral del cross V bar dot dl bar is equals to open integral SC del cross A bar dot ds bar. Option D, closed contour integral del cross A bar dot dl bar which is equals to open integral SC V bar dot ds bar. Now the question is given like this. Let's say here V bar is a vector and it is related to our A bar with this relation V bar is equals to del cross A bar. Now once again, same as our previous one, here also we need to recollect the concepts of our Stokes theorem and divergence theorem. So in Stokes theorem, so once again it is related to the Stokes theorem itself. So what is a Stokes theorem? Whenever we have a vector a bar, then the closed line integral of that particular vector a bar, that is line integral of a bar dl bar, is equals to open surface integral of del cross a bar dot ds bar. So whenever we have such type of relation, that is a closed line integral, you can relate that one with the open surface integral. So here what you have to do is you have to relate our v bar and a bar. So whenever we have that v bar and a bar relation, then obviously the answer is the correct one what we can choose. So replace our v bar with del cross a bar. So whenever we have that v bar, just replace that one with del cross a bar. So if you replace this v bar with del cross a bar, then this is the equation what we get on left hand side, but it is not same as our Stokes theorem. So option A is wrong. Go to the option B. In the option B, contour integral of a bar dot dl bar, which is equals to open surface integral of, instead of v, if you write del cross a bar, so del cross a bar dot ds bar. Just you compare this one with the equation of our Stokes theorem. Contour or the closed line integral of a bar dot dl bar is equals to open surface integral of del cross a bar dot ds bar. So clearly this satisfies our Stokes theorem, though option B is right. So correct answer for this question is option B. Now another question is given like this. A vector p bar is given by p bar equals to x cube y ax bar minus x square y square ay minus x square yz az. Which one of the following statements is true? Option A, p bar is solenoidal but not irrotational. Option B, p bar is irrotational but not solenoidal. Option C, p bar is neither solenoidal nor irrotational. Option D, p bar is both solenoidal and irrotational. So this is the question given to us. Now a vector p bar is given to us. P bar is x cube y ax minus x square y square ay minus x square yz az. He asked to check the solenoidal property and rotational property of this particular vector. Now we need to recollect the concept of divergence and curl here. When a particular vector is said to be solenoidal, when a particular vector is said to be irrotational or rotational. Now let us take a bar is a vector. If a bar is a vector and the divergence of that particular vector is 0, then it is said to be solenoidal. So whenever you are calculating the divergence, and if that divergence is equals to 0, simply it is said to be solenoidal. And for the same vector, if we are calculating curl and if it is equals to 0, then it is said to be irrotational, that it has no rotational property. So now what we have to do is we have to observe these two properties for this vector given p bar. So if you calculate this divergence for this p bar and if it is equals to 0, immediately you can say that this p bar is a solenoidal vector. And by calculating the curl, and if you said that it is equals to, if you observe that it is equals to 0, then it is said to be irrotational. For that, what we have to do is you have to apply the divergence and curl both to this particular vector p bar. Now in which coordinate system we need to consider this del operator? To consider this del operator in a given coordinate system, just you observe the unit vectors. The unit vectors are ax, ay, az. Since the unit vectors are ax, ay, az, the given del operator must be taken in a rectangular or Cartesian coordinate system. So how this del operator was defined in rectangular or Cartesian coordinate system? Just recollect dou by dou x of ax plus dou by dou y of ay dou by dou z az. So the divergence is nothing but the dot product between this del operator and p bar will gives you the divergence of that vector. Cross product between this del operator and p bar will gives us curl of the vector. So first we will examine the divergence, that del dot p bar. So directly I am writing. So in a examination, if you are taking the equation and substituting it in a step by step procedure, that may kill our time. So what we have to do is you have to directly observe what are the parameters which are given to us and how to solve the problem in a quickest way. So for that, just you examine itself. So ax dot ay, ax dot az, that's always they will be 0. Ay dot ax, ay dot az, always they will be 0. So what we get is only dou by dou x of or px. Px is the first term what we have, x cube y, plus dou by dou y of the corresponding term of y is minus x square y square. And the third term is corresponds to the az, that is dou by dou z of x square y z. So directly write down the equation. Since the differentiation is very easy to us, write down this one as 3x square y minus, since it is minus I am writing 2x square y minus, here it is minus x square yz. So place it as a minus x square yz minus x square y. So minus 2 minus 1 is minus 3 plus 3 0. So directly we got del dot p bar is equals to 0. Since we got del dot p bar is equals to 0, this p bar is a solenoidal vector. So one option is over. Next go for the second verification, that is del cross p bar, that I am considering this cross product for p bar. So consider the unit vectors in the given coordinate system, ax, ay, az, dou by dou x, dou by dou y, dou by dou z, and the components of our p bar are x cube y, second one is minus x square y square, third one is minus x square y z. Here I will give you a simple technique that don't go for the entire calculation. So here we don't require any answer, just what we require is the property of this vector. We don't require answer. So we don't require any equivalent of this one. So what we have to do is, if you observe any one of these terms, here we have three terms, one is in terms of x, y, z. So if any one of these three is 0, any one of these three is not 0, then immediately you can say that it is rotational. That what we are getting is a curl. Since we are getting this curl, you can say that it is rotational. So just observe this one for its non-zero property, that del cross p is not equals to 0, immediately say that it is rotational. Is equals to 0, immediately say that it is irrotational. So what I do is, just I will examine that one for one or two terms, that's in terms of x or in terms of y or in terms of z. So consider the first one, that is the x component, ax dou by dou y of minus x square yz. So dou by dou y of minus x square yz is just minus x square z, and this one dou by dou z of minus x square y square. Since it is the differentiation is with respect to z, what we get is 0, plus, not plus, minus ay, you may get something, but observe here, even for the first product what we are getting is ax into something, right? This is not equals to 0, what you can say. No need to go for the ay term and az term. So even if you are not taking that ay and az, you can say that this del cross p is not equals to 0. If it is equals to 0, you will say that it is irrotational. If it is not equals to 0, simply it is said to be rotational. Since it is rotational, what you can say is it is not irrotational. Now with the observation of this del dot p bar is equals to 0, you can say that it is solenoidal, and with the observation of del cross p not equals to 0, it is not irrotational. That is means it is rotational. That's what we can say. Now we need to choose the proper answer for this one. Del p bar is solenoidal, p bar is not irrotational. Now in the options given, the p bar is solenoidal but not irrotational. That is option A is correct option. Question number 4. The direction of vector A is radially outward from the origin with magnitude of A, that is magnitude of A is equals to k into r power n, where r square is equals to x square plus y square plus z square and k is constant. The value of n for which del dot A is equals to 0 is option A minus 2, option B 2, option C 1, option D 0. Now the vector is given like this. Magnitude of A is equals to K into R power N, and he mentioned clearly it is radially outwards, and R square is equals to X square plus Y square plus Z square. This equation gives a clear idea about in which coordinate system we are supposed to take that vector A bar. Since he mentioned clearly that A bar is radially outwards and the radius equation is X square plus Y square plus Z square is Z square, then we can say that the given coordinate system is a spherical coordinate system. So in the spherical coordinate system, we need to represent the vector A bar. For that, let us take the A bar is K R power N in the direction of R. In our notation, we took that one as capital R, but now in the problem it is small r was given, consider the smaller itself, no problem. So A bar is a vector K R power N, A bar is the vector notation of that A. The magnitude is K into R power N, and he mentioned clearly the divergence of that particular vector A is 0. So we need to calculate the divergence of that vector and make it equals to 0 to obtain the value of N, where K is some arbitrary constant. Now consider the divergence of A bar. Now in the basic synopsis, what we learned is this del operator can be applied in different coordinate systems. That can be taken in rectangular coordinate system if the vector is in rectangular coordinate system. That can be applied in cylindrical if the vector is given in cylindrical coordinate system. And since this is given in spherical coordinate system, we need to consider this del operator in spherical coordinate system. So consider the entire del operator in spherical coordinate system and apply that one to the A bar. Now here observation plays very important role, that in our A bar we have only radial term and we have no theta term and phi term. So what are the three coordinates in our spherical coordinate system? In their order they are r, theta, phi. So if you are considering any vector, it may contains a r term, a theta term and a phi term. Now observe here, A bar contains only a r term and the a theta term and a phi term are 0. That what you can take. So in the dot product, so you may not get any a theta term and a phi term. So when you are considering this divergence, only a r term will play important role and the remaining two terms can be neglected. So don't go for the calculation of remaining two terms, that is dou by dou theta of something, dou by dou phi of something, no need to consider it. Directly consider the a r term and solve the problem. So here, what is the first term? That is the a r term in terms of our del operator. That is 1 by r square dou by dou r of r square a r. That what we need to consider, where a r is the component of a in radial direction, which is equals to 0. That is given in our problem, right? Now which is equals to 1 by r square dou by dou r of r square into a r can be replaced with k r power n, which is equals to 0. This is simply 1 by r square dou by dou r of, this is k r power n plus 2, which is 0. So if you take the differentiation of this one, what we get is 1 by r square, the differentiation of this one is n plus 2 r power n plus 1, which is equals to 0, and a constant k also will be there. If this is 0, just we need to examine this equation. If you examine this one, the radius term and the constant k, so these two are not equals to 0, and since the radius is an arbitrary one, this is also not equals to 0. So r power n plus 1 is not equals to 0, k by r square is also not equals to 0. So obviously what we can say is the term n plus 2 is equals to 0. That is n plus 2 equals to 0 gives n equals to minus 2. So this is the answer. Question number 5. A vector field D equals to 2 rho square a rho plus z az exists inside a cylindrical region enclosed by the surfaces rho equals to 1, z equals to 0 and z equals to 5. Let S be the surface bounding the cylindrical region. The surface integral of this field on S is, so no options were given, we need to write down the solution. Now the vector D is given to us. D is equals to 2 rho square A rho plus Z AZ. And the value of rho is 1 and Z is extended from 0 to 5. We need to calculate the total closed surface integral of d ds. So for that, examine this one, and if you draw the figure for this, that is very easy or convenient to solve the problem. So what we do is we will represent a pictorial representation of our cylinder what we have. As I said, this is a cylindrical coordinate system. Since rho z are presented and rho is given, z is given, we need to take this one in our cylindrical coordinate system. So for our convenience, draw a cylinder. Here to draw that cylinder, take rho is from 0 to 1, that is the radius of the cylinder is 1 and the cylinder is extended from z is equals to 0, z is equals to 0 means this xy plane, to z is equals to 5. So exactly at this location z is equals to 5 and at this location z is equals to 0 and the radius of our cylinder is 1. So rho is equals to 1. We need to calculate the total closed surface integral of this one. So for that we need to examine how many surfaces are there. To solve this problem, actually we have two different methods. So we will discuss those two methods also. One is the conventional method, taking the surface integral and solving the problem. Another one is a shortest method. So by using our very beautiful theorem, Stokes theorem, you can solve that one, right? So we will discuss those two methods also, no problem. Now let us consider this surface. How many surfaces are there? Let us consider this cylinder. For this cylinder, we need to examine how many surfaces are there. If you observe this cylinder, it contains three surfaces. One is this entirely curved surface, another one is the top surface, the third one is bottom surface. If you consider the curved surface, then you can observe the cylinder shape. If you observe the top surface, just it is a plane which is located at z is equals to 5. Another one is the bottom surface, it is also a plane which is located at z is equals to 0. So the total surface integral, here it is a closed surface integral. The total surface integral includes the integration of d around the curved surface, integration of d along this top surface and integration of d along that bottom surface. So what I do is, I will write this one as the summation of those three. So the total closed surface integral of d ds is equals to the surface what we are considering for curved d ds plus the surface what we are considering for top d ds plus the surface what we are considering for bottom d ds. Here clearly observe, in all these cases d is same, or so only one d function is given to us, but this ds will vary. The differential surface what we are considering for the curved one, the differential surface what we are considering for the top one, and the differential surface what we are considering the bottom one will vary. Now we need to examine what are differential surfaces for top, bottom and curved. As I said, if you want to write down the differential surface for any direction, we need to remember the differential length equation. So remember the differential length equation in our cylindrical coordinate system. In the cylindrical coordinate system, the differential length is given as d rho a rho plus rho d phi a phi plus dz a z. So this is the differential length equation. Now examine in which direction you require differential surface. The differential surface is required in curved direction. Curved direction means always in radial direction. That the differential surface direction is away from that particular volume, that is in radial direction, rho direction. So if you require differential surface in rho direction, close this term and write down the components of remaining two. So here I am writing differential surface in rho direction, which is equals to rho d phi dz. Rho d phi dz in the direction of rho. Just close it and the components of remaining two vectors will be written here. Next, the differential surface for top we require. So differential surface for top. For the top, just you observe the direction. If you are taking the top surface, the direction is always in positive z direction. Since the direction is always in positive z direction, consider differential surface in positive z direction. That is, close this term and the components of remaining two will be multiplied. Then if you multiply these two components, then it becomes rho d rho d phi in the direction of positive z. That's Az is the positive z direction. In the same way, the differential surface for bottom I am taking. So if you take the differential surface for bottom, now once again just you examine the direction of the differential surface. The differential surface is always away from the volume. So the differential surface what we are considering is in negative z direction. So negative z direction means the same quantity we get with a negative sign here. That is minus rho d phi in z direction. So these three are the differential surfaces what we need to consider for corresponding components. So d dot this ds here we need to consider for curved surface. D dot this ds we need to consider here. D dot this ds we need to substitute here. And while integrating this one, we need to take a double integral. Since it is a surface integral, so double integral with the values which are given in our problem will give you the answer. We will solve that one by one. So for the curved surface, I am calculating the differential surface. So differential, this particular integral quantity. So for curved surface, just you substitute the values of d and ds here. Then what you can write is, so for time being just you leave the limits, we can write later. D is 2 rho square a rho plus z a z dot, this differential surface will be considered in curved direction, that is nothing but the rho direction, rho d phi dz a rho. So rho d phi dz in the direction of rho, that what we need to consider. So which is equals to double integral of, since we have only a rho here, a rho dot a rho term becomes, the remaining term becomes 0. So it is 2 rho cube d phi dz. A rho dot az is always 0, so neglect it, don't write down that one. 2 rho square into rho is 2 rho cube, d phi dz is the term what we have. Now what we have to do is, so don't go for any other calculations or analysis, just you observe the differential quantities here. So if you want to simplify this one, we need to integrate this. If we want to integrate, so some quantity must be there, that is a differential quantity. Here the differential quantities are phi and z. So here we need to substitute the limits for phi and z. So the simplest way for substitution of limits for phi is equals to 0 to 2 pi. For the entire cylindrical surface is 0 to 2 pi, and z is from 0 to 5. Just take z is from 0 to 5. So if you simplify this one, since there is no rho component for the different integration, rho can be treated out as a constant. So 2 rho cube, that's what I am taking. With this d phi, if you integrate, d phi will becomes phi, and the phi limits are from 2 pi to 0. So what we get is 2 pi. For this is for phi into z. So since there is no another z term, only z what we get. Z is taken from phi to 0. So what we get is phi. Now what is the value of this rho? So to simplify this one, this rho is also essential. Rho is given as 1. Since rho is given as 1, substitute here, then what we get is 5 into 2 10, 10 into 2 20 pi. So this particular quantity is for only curved surface. So what we get is 20 pi for curved surface. Still we have two more surfaces, that is the top surface and bottom surface. We need to substitute those two also, right? Now the surface is integral for top. What I am considering, yes, top, substitute this d 2 rho square a rho plus z a z dot, the differential surface what I am considering is for top. For top, this is the differential surface equation, rho d phi a z. So rho d phi a z. Now once again this z term only remains for us, the remaining all terms will be vanished. Since the dot product gives you 0, no need to consider them. So the double integral of this one is z rho d phi. So az dot az is 1, z rho d phi. Once again I am saying, don't go for any mathematical or rigorous analysis. Just you observe the differential quantities what we have here. The differential quantities are d rho and d phi. Since the differential quantities are d rho and d phi, we need to take the limits for rho and phi only. nothing more than that. Now, what is the value of rho? Rho is given as 1, even though it is given as 1, it is extended from 0 to 1. So, the rho value is simply 0 to 1 and the phi value is once again 0 to 2 pi. For the entire surface, closed surface, we are considering this phi as 0 to 2 pi. Z can be treated as constant here. Now, what is the Z value for this top? That we need to observe. For the top surface, always the Z value is 5. So, this Z can be treated as a constant and replace this one with 5. So, this can be simply given as Z. Instead of Z, I am writing directly 5 and rho d rho. Rho d rho is nothing but rho square by 2, that is taken from 0 to 1 multiplied with respect to phi. If you are integrating, phi is from 0 to 2 pi, what we get is 2 pi. So, the direct integration will give us the answer. If you take this rho limits are from 0 to 1, what we get is 5 into 1 by 2 into 2 pi, which is equals to 2 will be cancelled, 5 pi. Just if you remember the previous one, for the curved surface what we get is 20 pi, for the top surface what we get is 5 pi. Now we have one more surface, that is the bottom surface. For that bottom surface also we are supposed to calculate the total vector, right? Now for that bottom surface, once again substitute the bottom ds here. For the bottom surface, if you consider this ds is negative sign of this one. So the entire quantity for the differential surface is same except the direction. Now don't go for any other, just you observe what we are taking. So we are doing dot product with az, right? So the z remains for us. Now what is the value of z for the bottom? Z is equals to 0. So the bottom is exactly placed at z is equals to 0. Since z is equals to 0, if you substitute that z value, this entire term vanishes. That what we have to do is, in the examination, we need to analyze. Don't go for the calculation of this entire thing. So if you calculate that one, that may kills our time. So what we have to do is just examine this. Az dot az remains for us. In that one z we have. So if you substitute z is equals to 0, the total integral is now becomes 0. Now examine this one. We calculated the particular quantity along the surface of our curved surface of the cylinder, top surface of the cylinder and bottom surface of the cylinder. For the top surface, what we get is 5 pi. For the curved surface, what we get is 20 pi. And for the bottom surface, what we get is 0. So now the total particular quantity which is passing through or the leaving that particular surface, the closed surface integral of dds is 25 pi. So this is the answer what you have to write there. That if the answer is given in terms of simple numericals, we need to substitute the value of this pi also and we have to simplify that one. So this is the conventional method what we did. In the conventional method, what we took is the entire surface, the top surface, bottom surface, and we calculated a particular quantity for these three surfaces and we added them. Then we will get the total closed surface integration of that particular quantity. If we solve this problem in our conventional way, what we are getting is 25 pi answer, but the time it is taking approximately 20 to 25 minutes. So in any competitive examination, taking that much time is not correct one. So what we have to do is, you have to search for an alternative method. So how to solve this problem in very easiest way. So for that, just you observe what is the quantity given to us. Here we need to calculate the surface integral for this particular quantity, and this surface is a closed surface. Since it is a closed surface, we need to recollect a few theorems which are related to the closed surface, right? So recollect our divergence theorem. So any closed surface can be related to the volume integral. Here d bar is a vector. Since it is a vector and it is calculated for the closed surface, you can take the equivalent of that one in our divergence theorem. So directly I am writing this one using our divergence theorem. So any closed surface can be related to volume integral of r del dot d dv. So instead of calculating this closed surface, if you calculate the volume surface, this problem will become very easy. Not only to this one, so whenever it is required, taking a contour or taking a closed surface and calculating in all directions, it will kill our time. So what we have to do is take the easiest one. So for that, what I do is, I will take this divergence of d, and by calculating this volume integral, I will try to get the same answer. So for that, what we require is this dV term. So what is dV in our cylindrical coordinate system? That is the differential volume in cylindrical coordinate system is d rho, rho d phi, dz. That is d rho, rho d phi, dz. That is rho d phi, dz. So keep this aside. Now come to your divergence of d. Del dot d I want. So this del operator will be taken in our cylindrical coordinate system. In the cylindrical coordinate system, consider the del operator, apply here, then what we get is this del dot d. In cylindrical coordinate system, the del operator is 1 by rho, dou by dou rho of rho, a rho. A rho is nothing but here d rho, rho term 2 rho square into 2 rho square plus dou by dou phi is the next term what we get. Dou by dou phi of AFI dot FI. So AFI dot FI is not there. So directly neglect that one. No problem. Next one is dou by dou z of our z component z. So if you calculate this one, just you examine what we get. That is 1 by rho dou by dou rho of this is 2 rho cube plus dou by dou z of z. So which is equals to 1 by rho of this dou by dou rho is nothing but your 6 rho square plus 1. Rho will be cancelled here, 6 rho plus 1. So the divergence of this particular term is 6 rho plus 1. Now what we do is we will substitute this divergence here and this dV here. So by substituting this divergence and dV, easily we can calculate this one. So this is the divergence term what we have. Substitute here. Then the total volume integral of the divergence term is 6 rho plus 1 and dV term is rho d phi dz. So here what we are doing is we are taking the equivalent of this surface integral and we are taking the divergence of this term and volume integral and solve this one. Observe the volume integral. In the volume integral what we have is the 3 integrations. These 3 integrations are meant for rho, z and the third one is phi. So we need to substitute all the limits here. Substitute the limits for rho. So rho is taken from 0 to 1. The radius of our cylinder is taken from 0 to 1 and phi is taken from always 0 to 2 pi for the entire closure surface and z is taken from z is equals to 0 to 5. So bottom is at 0 and top is at 5. And if you simplify this one, what we get is 6 rho square plus rho d rho and there is no phi term except d phi, z term is dz. So we need to integrate this one. Just you observe what is the integration of that one. Here the integration of that term, the integration of this term will be simplified like this. So initially do with this phi and z. So if you do with this phi, so d phi is phi and the phi limits are from 0 to 2 pi. So what we get is just 2 pi. And with respect to z, the limits are from 0 to 5. So simply what we get is 5. Now the integration is only for 6 rho square plus rho, that is with respect to rho. So 6 rho square is 6 rho cube by 3 plus rho square by 2. The limits are from 0 to 1. So what we need to do is just we need to evaluate this, which is equals to 2 pi into 5 is 10 pi and this is just 6 by 3 plus 1 by 2. The lower limit 0 is always 0. So which is equals to 10 pi into what is this one, 2 plus 1 by 2 is 5 by 2. So 2 will be cancelled, 5 into 5 25 pi. So this is the answer what we got in our earlier step. So by considering the entire surface and calculating the surface integral for curved surface, top surface and bottom surface will give us the same answer, but it takes long time. Instead of that one, if you take the volume and for the entire volume how this is varying, this particular d can be calculated, that we can observe that one using our divergence theorem. In an easiest way you can obtain this answer. So this is our solution for our question number 5. Question number 6. If a bar is equals to xy ax plus x square ay, then the closed line integral of a dot dl over the path shown in the figure is. Now the question is like this, a bar is given which is as xy ax plus x square ay, and here the contour is mentioned in this direction. This is the contour which is given for us, and the dimensions of that contour are also given. It is from 1 by root 3 to 2 by root 3 for x and 1 to 3 for y. We need to calculate the closed line integral of this a bar dl. Now if you want to calculate the closed line integral of that a bar dl, the conventional method is like this. So what we have to do is, we have to consider this closed path is in this direction for this one, in this direction for this, and in this direction for this particular part, and in this direction for this particular part, and add all those things to get the total. That is the conventional method what we have. Then the closed line integral is this path plus this path plus this path plus this path will give us the answer. But don't go for that conventional method. If you go for that conventional method, once again as we discussed, so we need to spend lot of time there. So for that, examine the surface which is formed by that closed path. If that particular surface is known to us, then go for the equivalent of that one. So once again remember that whenever we have a closed path, examine the surface first. So if we know what is that particular surface, then you can go for the equivalent of this closed line integral. So how to obtain the equivalent of closed line integral? The closed line integral can be obtained using our Stokes theorem. The equivalent of that one can be obtained using our Stokes theorem. So clearly a closed contour integral of a bar dl can be written as open surface integral of del cross a bar ds. So what you can take is del cross a bar. If this ds is known to us, you can use this simple formula, right? Now observe the closed surface what we have. This is the closed surface what we have, and the equation of this closed surface and the direction of that closed surface, these two we want. This closed surface is purely placed on xy plane. Since it is placed on xy plane, a normal direction to this one is always like this. That is, it is coming towards the coming out of the plane of both. If it is coming out of the plane of both, and if you take the coordinate system, it is a right-handed coordinate system, then this surface has a direction of z. So you can replace that direction with az. So already, so we know what is the differential surface which is in that xy plane, which is on that xy plane, that is dx dy. So the differential surface what you can consider in this case is just dx dy in the direction of z. Since the differential surface is known to us, go for this method. So if it is not known to us, just go for the conventional method, right? Now the calculation of this curl is remained for us. I will calculate the curl of a bar. So del cross a bar is equals to, so what is the vector in a rectangular coordinate system? Ax, ay, az, those are the vectors what we have. The components of first vector are dou by dou x, dou by dou y, dou by dou z, and for a, the components of ax are xy, and the components of y are x square, and for the component of z we have no term, that's why I have replaced here 0. So now clearly observe, you can calculate, you have this ds and you can calculate cross product of our del with a bar. Since we have these two, just I am taking this simple method. Take this one Eax, just I am simplify this one. So dou by dou y of 0, 0 minus dou by dou z of x square 0 minus ay into dou by dou x of 0, 0 minus dou by dou z of xy 0 plus az into dou by dou x of x square, it is 2x minus dou by dou y of xy, it is x. So if you take this curl, so most fortunately what we are getting is 0 for these two, and this one what we get is just x az. So del cross a bar is known to us, ds is known to us, substitute here. So which is equals to, that is the closed line integral of our a bar dot dl is equals to surface integral I am considering, just leave our limits for some time. Instead of this del cross a bar, I can write this x az dot, instead of this ds, what I can write is dx dy a z. Now a dot az is 1, the remaining term is double integral of x dx dy. Now we need to substitute the limits for solving this one. So what are the limits of x and what are the limits of y? Once again I am saying, don't go for the analysis, just you take the differential quantities. The differential quantity is x, so we need to substitute the limits of x. The differential quantity is y, so we need to substitute the limits of y. So what are the limits of x? The x always can be taken from 1 by root 3 to 2 by root 3. So x is equals to 1 by root 3 to 2 by root 3. Y can be taken from 1 to 3. So y is always from 1 to 3. So if you simplify this one, what we get is, instead with this integration, y is from 1 to 3 and x dx is x square by 2 from 1 by root 3 to 2 by root 3, which is equals to, now y is from 3 to 1, just it is 2, and x square by 2 is from 2 by root 3 to 1 by root 3, that is 4 by 3 by 2 minus 1 by 3 by 2. So the upper limit is 2 by root 3 x square, 4 by 3 by 2 minus lower limit is 1 by root 3, that is 1 by 3 by 2, which is equals to 2 will be cancelled. Directly the answer what you can write is 4 by 3 minus 1 by 3. 4 by 3 minus 1 by 3 is 3 by 3, 1. So the option what we have for this one is right. So in the question, the options A is 0, B is 2 by root 3, C is 1, D is 2 by root 3. So here what we got is answer 1. So option C is right. Given f bar is equals to z ax plus x ay plus y az. If S represents the portion of the sphere x square plus y square plus z square is equals to 1 for z greater than or equals to 0, then the surface integral of del cross f bar ds is. Now here the question given is f bar is equals to z ax plus x ay plus y az, and clearly what he is saying is he is calculating, or what we want is the calculation of this particular quantity for a surface. So what is the surface which is given to us? The surface which is given to us is x square plus y square plus z square is equals to 1. So clearly observe the surface which is given to us. Here this represents a spherical surface. If you take the graph of this one, what we get is a complete sphere. But this sphere was mentioned only for z greater than or equals to 0. Since it was mentioned for only z greater than or equals to 0, clearly observe this is not a closed surface. This is an open surface, right? So what I do is, for our convenience, I will draw our open surface which is meant for us, or so which is given to us. The x square plus y square plus z square is a sphere with origin as its center point, and the radius of that sphere is 1, and it is placed above the z, that's the xy plane, it's above the xy plane. For z greater than or equals to 0, it was described. So clearly this is the sphere what we need to consider. So the radius of the sphere is 1. So it is placed on xy plane in such a way that the half sphere, so what we can consider is on above the xy plane, is above the xy plane, right? Now clearly observe what are different portions of this particular sphere. This particular sphere will forms an open surface. The bottom is opened. There is no closed surface here. So the bottom was opened, and if you observe, the bottom forms a closed line. The surface what we are considering is on xy plane, and the bottom forms a closed line, and that closed line clearly is on xy plane. Now if you observe, what is the shape of that closed line? Is a circle. So here what you can take is, for that closed line, the equation is a circle equation. So what I do is, I will write down the equation of that circle for that closed line, that is x square plus y square is equals to 1. For our convenience, what I do is, I will take the equivalent of this x and y in cylindrical coordinate system. So actually this was given in a rectangular coordinate system. The shape is given in spherical coordinate system, or the sphere. And for our convenience, you can take the equivalent of this one in cylindrical coordinate system. So here what we are doing is, we are using as all the coordinates or all the parameters as our convenient. So let us take x is equals to, the radius of this one is 1, that is nothing but rho cos phi. So that what you can take. In the same way, y is equals to rho is the radius, 1 sin phi. So keep them aside. If they are required, we can use here, right? Now come to the problem which is given to us. In the problem, what we have is a surface integral of del cross f ds. Here it is an open surface integral. Now recollect the Stokes theorem what we have. In our Stokes theorem, any closed line integral can be related to the open surface integral. So the reverse of that Stokes theorem here we are applying. The open surface integral can be related to the closed line integral. Since we have a curl equation as a cross product with this del and f bar, you can relate this one with our closed line integral. So the surface integral what we have is equals to, that is del cross f bar ds is equals to closed line integral, that the closed line that's clearly covers our surface what we have, closed line integral of f bar dot dl bar. So instead of calculating this one, as taking curl and applying curl here and ds, we don't know what is the direction of that particular ds. So instead of calculating this one, if we calculate the closed line integral of f bar dot dl bar, the problem will becomes easy. So what I do is, I will calculate this one. For that, consider the closed line integral of f bar dot dl bar, which is equals to a line integral as it is I am writing. F bar is zax plus xay plus yaz dot, instead of that dl, so take the equation which can be written in our Cartesian coordinate system. The dl expression in our Cartesian coordinate system is dxax plus dyay plus dz az. So now go for the dot product. So what we get is here, so line integral of zax dot dxex, this is z dx plus, so line integral of, just line integral will be splitted here, xay dot dyay, that is x dy plus the line integral that what I am shifting here, that's a splitting here, this is y dz. So this is the equation what you can write for this f bar dot dl bar. Now examine this equation again. So if you examine this equation, clearly you can understand what are the limits we need to substitute to calculate that line. Here the line was taken, the closed line what we are considering was taken on the xy plane. Since it was considered on the xy plane, the value of z is always 0. So if the value of z is 0, then you can make this term to 0. Z multiplication is there, right? Here also, since z is 0, dz is also 0. So this term is also can be treated as 0. So if you take this entire closed line integral, now this becomes only just a line integral of x dy. So if you calculate this particular quantity, then that will be equals to the answer. So how to calculate this one? So the term left for us is the line integral of x dy. So instead of x, now substitute this cos phi. That's why the equivalent will be considered in our cylindrical coordinate system is most useful here. So directly taking instead of this x and y, and we don't know what is the limit of this L. Since it is not a simple straight line, we can't substitute the limit of our y here. That's why what I am doing is, I am considering this x and y in our cylindrical coordinate system. So which is equals to, so line integral of, instead of x, what I do is, I will write cos phi and dy. Here from this one, I will calculate dy. dy is equals to, the sin phi gives cos phi d phi. Substitute here cos phi d phi. So now the entire expression was simplified. So what we got is a line integral of cos phi into cos phi is cos square phi d phi. So which is equals to, now I will substitute the limit. Here what we are doing, we are integrating this one with respect to this phi. So the phi is taken from 0 to 2 pi for an entire circle or the entire line what we are considering. For the closed line, the phi will be considered from 0 to 2 pi cos square phi d phi. Directly we have a relation for this one. The answer what we get is pi. So here, as I said, so taking the direct term for the calculation purpose, if you take the equivalent term, then the problem will becomes easy. So here we need to examine, So which one is most suitable and which one can be taken in easiest way? So if we take that particular term and substitute here or replace here, then the calculations will become easy. So here these are some of the problems what we have, and with the knowledge of these problems we can apply as a different parameters on our electrostatics and magnetostatics are time varying fields. Using